Hello people, in this video I would like to talk about a second order transfer function and how that transfer function responds to a step input. Um, Last video we talked about first order response, and this time we are moving a step forward and trying to analyze the second order transfer functions. First of all, let me draw and visualize how a second order system can be written and etc. So first of all, since I said we will work with unit step inputs, we have 1 over s, right? Unit step. And let's draw a rectangle here, and we will put our transfer function inside. Let's say this is gs, and we have the output cs. All right. To indicate, to form a basic second order transfer function, we can write this. So a constant b over s squared plus as plus b. So this is the most general formula to represent your second order transfer function. But the most important, or let's say the difficult part to analyze second order transfer functions is, comparing to the first order functions, they can exhibit different kind of responses. How? By the location of the poles. So this s squared plus as plus b part is the denominator part, and this is the equation that creates our characteristic of the response. So I draw some different colors and maps to make you understand how the things change as we move our poles to left, right, up and down. So let's start with the purple one. So the left side you see a pole zero map, where this is j omega and this is the real axis, and at the right side we have a step response graph where we have as output ct, which is the inverse Laplace of cs as we draw above, and time goes 5, 6 and moving to infinity. So first of all, let's say you have a transfer function, which is the purple one, and okay, let's move that into later. But if you have poles at the imaginary axis, a complex conjugate poles at 3i and minus 3i, you will have a response like a sine wave or cosine wave. By the way, I will name them, but I will tell you about them later. So the name of this response is undamped response. Undamped response. Keep in mind, this is undamped response. All right. If you have two poles at the real axis, like minus 8 and minus 1, you will have a response which is too slow but reaches out to a final value correctly. So this is the green one. We name it overdamped. Overdamped. And also, if you have poles which have both real axis parts and imaginary axis parts, like the dark blue one, you will have a response called underdamped response. And lastly, if you have two poles at the same exact location, like minus 3 here, we will name it critically damped. But how we do this segregation, how we do this like mindset, how we change, how we separate those kind of, let's say, responses, and how we can match them with our poles. So as I wrote down here the general expression for second order transfer functions, we have one more which helps to lead ourselves to analyze those kind of responses and the corresponding pole combinations. So let's start with the green one, okay? Green one. But first of all, I will write down the general expression for second order transfer functions. For now, I just write it down and I will tell you about it in a few seconds. So GS equals Vn squared over S squared plus 2 zeta Vn plus zeta Vn S plus Vn squared. This is the general expression for second order transfer functions. Vn is our natural frequency, but for now just disregard it. On this video we will more focus on zeta. Zeta is the one like a tail, long tail. I mean, it's so hard to draw, but it's something like this. This is zeta. Also you can call it the damping ratio. You see guys, there's a similarity between the words damping ratio and overdamped, critical damped, underdamped, and undamped. So yeah, we can say with respect to zeta, the damping ratio, our step response graphs change, right? Okay. So let's start with the yellow one, okay? Since we said Vn squared is the value here, like 9, I can say Vn is 3, right? And since we have 6 there, I can say 2 zeta Vn is 6. 3 equals, I just divided into 2. Zeta Vn was 3. So I can say my zeta is 1, right? So here we can understand, we can sense something. If we have zeta as 1, we will have a critically damped response. Okay? Let's move on. Let's move on to the purple one. Here, again, we have Vn as 3, since there is 9. The square of 3 is 9. But be careful, there is no S component, so there is no contribution of S into this denominator. So I can say that part is going to be 0, which is 2 times zeta times Vn was 3. In order to have 0, my zeta should be 0, right? And you see guys, if we have zeta as 0, we will have an undamped response. The response is not damped and doing oscillation like this. You can say, isn't that unstable? No, we call it unstable on this level if it reaches out to infinity, but it doesn't go to infinity. It makes some oscillations inside some certain values. Let's say here is 2 and here is 0. It's undamped but restricted. It doesn't reach out to infinity. Let's go to green one. Vn as again is 3. 9 equals 2 times zeta times 3. So I can say zeta is roughly 1.66. Okay, so it is actually zeta here more than 1. Okay, and if your zeta is more than 1, you will have a response called overdamped. It's pressurized so high that it cannot go to the final value so quickly. It is so slow, but finally reaches out to the final value. And at the blue one, let's find out again. So Vn again is 3. 2 equals 2 zeta times 3. So zeta is going to be something like 33, right? 0.33, which is less than 1. All right. So I think you can just form something in your mind. If you have a zeta value less than 1 and more than 0, so this is, you will have a response called underdamped. It does a little bit overshoot here, and do some oscillations and reaches out to final value to 1. If you have a zeta value which is more than 1, okay, your response going to be slow. By the way guys, don't forget this. If you have an underdamped response, take a closer look here. the blue one, the underdamped one, has moved on to the final value so quicker than the green one. Like green one can reach out to the value like in 4 or 5 seconds, but on the other hand, the underdamped one reaches out at least like in 0.5 seconds, right? In half second. So if you make your zeta go higher, your response will be slow, but there will be no overshoot. If you make your zeta less than 1, you can't you can't pressurize your response. It will go quick, but it will display some oscillations. If you have your zeta as 0, there is no damping. So you let your response just swing around by itself, do some sine waves, right? And lastly, if you have zeta is 1, zeta is directly 1, you will have the response called critically damped. You can see this is kind of a combination of the green one and also the blue one. No surprise, blue one is less than 1, green one is more than 1, and the yellow is exactly 1. And we call it critically damped response.